Okay, so we're going to continue with the first example that we did in chapter 9. And you have the ages, guys. I'm just going to put them there. 9, 10, 11, 12. And then you have the number of irrelevant responses. These are the number of irrelevant responses. And we found out that there is a strong positive linear, strong negative linear relationship between X and Y by finding R. R was very close to -1. That's the R that we find. So among the members of this sample, guys, we feel that there is a strong connection between the age of the child and the number of irrelevant responses. The question is, guys, would that apply to the entire population of young students aged 2 to 12? Can I generalize and say for any child between age and 2 and 12, it's the same connection that we got from this sample. It's going to apply, just to the entire population of children whose age is between 2 and 12. It might apply, it might not apply. For example, guys, if I say if my students in my statistics class attend an extra couple hours a week, just of workshop in statistics, they're going to do better on next time they take the test. Can I generalize and say this is going to work for all students? Probably it will work, probably it will not work for all students. We have to perform what we call a hypothesis test to check. And the same thing here, guys. We have a data from 1, 2, 3, 4, 5, 6, 7, 8, 9 children that show that there is a connection between their age and the number of irrelevant responses. The older they get, the lesser the number of irrelevant responses. Can I say that for any children, all children, or the population of all children? Well, probably I can apply it, and probably I can't. The only way to find out, guys, is to perform a hypothesis test. So R is called the sample correlation coefficient. And we can find it using technology. But there is another correlation coefficient. It's called the population correlation coefficient that we need to test. And let me tell you what we call it. It's called DRO. This is the sample we can find using technology. This one, guys, you can never find because it applies to all the children. And in order to find RO, I have to have a data for every single child age 2 to 12 and have them take the standardized test and get their responses, which is almost impossible because you're talking about millions and millions. So this is for the population correlation coefficient. We're going to learn how to test this one. And the test is very straightforward. You will see how we're going to test this one. But we need to test the population correlation coefficient. Just like, guys, when you tested the mean in chapter 7, but you were given X bar. You were given data from the sample, but you were asked to test the population mean. And then you were given P hat, which is proportion from the sample, and you were asked to test the population proportion. Or you were given information about two samples, X1 bar, X2 bar, and you were asked to test the difference between two means, mu1 and mu2. So it's the same thing. You're going to be given information from the sample, and you're going to be asked to test the population correlation coefficient. So R will be giving, we're going to use R to test the population correlation coefficient. So the population correlation coefficient will tell us about how strong the relationship between the X and Y for the entire population, not just for the sample. Okay. And here is how we set up this test. Let me show you. There are 3 ways to set up the hypothesis. It's all in the handout. If you don't want to write notes, that's fine. Either it's going to be this, or it's going to be that. And can you guys tell me what's the last one? That should be easy.
Equal and not equal.
Yeah. Now, why against 0? Because we know if R is close to 0, correlation is weak. If R is away from 0 and close to 1 and -1, correlation is strong. And here, less than 0 means you are away from 0, but from the negative side. Greater than 0, you are away from 0, but from the positive side. Not equal to 0 means you are away from 0. It could be from the left or from the right. So in the alternative hypothesis, the correlation will be strong because this is where the inequality that says we are away from 0. So we write here, we don't write a claim where the claim is, we just write this statement here, correlation is significant. Here we write correlation is significant. Here we write correlation is significant. Now let me show you here. Let's read this one. Equal to 0. Equal to 0, you know, guys, when I defined R, I told you if R is equal to 0, that means, or very close to 0, correlation is very weak. So here we write correlation not significant. Here, rho is at most 0, less than or equal to 0. So you hear me, guys, saying equal to 0. That means it's on the weak side. So we write correlation not significant. And here, same thing in the null hypothesis, correlation not significant. So you don't have to worry a claim or no claim, just not significant, significant correlation. If you can support the alternative hypothesis, then there is a correlation. If you cannot support the null alternative hypothesis, then there is no correlation. So this is the first step in the hypothesis test. And if I go back to part D and show you what he's asking for. He's asking at the 1% level of significance test for negative correlation. So if I show you the 3 choices, which one would you choose? Or even if I go here, this is negative. This is a positive. Look, negative means less than 0. A positive means greater than 0. And this is correlation, test for correlation, either positive or negative. So if he asks you to test for negative correlation, this is your null and alternative hypothesis. If he asks you to test for positive correlation, that will be your alternative and null hypothesis. And if he asks you to test for correlation, then that will be your null and alternative hypothesis. And why do you guys think that he asked us for negative correlation here? There is a very, very good reason why. Negative correlation means there is a strong negative relationship between the values of X and the values of Y for the entire population. Why did he say negative, not a positive correlation? Because R turned out to be what? Positive or negative, guys? R turned out to be negative. So it makes sense to ask for negative correlation. So our null and alternative hypothesis is going to be this one. Okay, so the first step of the hypothesis test here, it's going to be HO, HA, positive correlation, I'll put there, and I write correlation is significant. It's just like I did before. And here, guys, you just write down correlation is not significant. And you will use this language in your conclusion. All right, so that's step number 1. I'm going to show you how to proceed with this problem using technology, but then I'm going to do it by hand, because when you do your homework by hand, you're going to come across some steps you're not just done by hand, and it's not difficult. You will see that. So let me show you how to perform the test. You already have the data X values in L1 and L2. So if you're ready for the test, let's show you how to do the test. So turn the calculator on. My battery is low. You go to stat. Just like in chapter 7 and 8, guys, you did do tests. And I would scroll up, not down. Any guess, guys, where do you think the test is? Just give me a good guess. You should be able to say which one it's going to be pertaining. This is only one function that we'll use in chapter 9. Is it A, B, C, D, E, F, G, H? Any ideas? What's the title of the chapter, guys? It is indeed F. We're doing linear regression, and it's a t-test. Exactly. So, guys, you're going to see that this formula even can find r and r squared and find the equation of the line. It will do everything for you. So let's go to it. That's the only one for chapter 9. And enter. Okay. It's asking me where's the X values. I put them in L1, we're good. Y values, L2. And before you hit calculate, you need the alternative sign, guys. And the alternative sign is less than 0, as you agree with me. It is right here. We're testing for negative correlation. Okay. I'm done. That's all I need. Okay. This is step number 2. Test the statistic, negative 10.743. So that's step number 2. There you go. It's right here. Using TI-84 linear regression t-test. So T is negative 10.74. That's step 2. Step 3, the p-value, guys. You can see it right here. You can see 6.656 E minus 6. Please don't ignore the E minus 6. Means you have to move the decimal 6 places to the left, so it's going to be 0. Which is less than alpha. So step 4. Reject what? HO. And step 5. There is enough evidence. I don't even need to know what alpha is because the p-value is so small, but what did he say? 1%. At the 1% level of significance to conclude that correlation is significant. Between the age of the child and number of irrelevant responses. Irrelevant responses on the test. That's it. On a standard test. It's all written there, guys, but I just wanted to show you again. how to do this. If you fail to reject HO, guys, there is one thing you change here. So only you have two statements in step 5. Either you use this statement or you use another statement. If you fail to reject HO, you say there is not enough evidence to conclude that correlation is significant. So we don't say support the claim and reject the claim. Either you conclude that correlation is significant or you don't conclude that correlation is significant. So this is one statement. If you fail to reject HO, guys, you just do the exact same statement, but just add not here. There is not enough evidence at the 1% level of significance to conclude that correlation is significant. So it's always about whether significant means there is correlation. Not significant means it's weak correlation. That's what I'm trying to explain to you here, guys. Let me show you what the calculator, the program showed us in addition to what you noticed there. Oops, let me just go back and do it one more time. Stat, tests. Okay, I'm gonna run the test again. There you go. So we got y equals a plus bx. I'm gonna write it down. And the calculator gave me degrees of freedom. It gave me A, which is 17.3. If I round it to 1 decimal. It gave me B, which is negative 0.96. It gave me S, which we'll talk about it in a little bit. And there is an arrow, guys, pointing down. So it's asking you to keep going. Oh, there's R square and here's R. R square is 0.94. And R is negative 0.97, as you can see, guys. So if you don't want to use linear regression AX plus B from calc, you can use this one and get the information that you want. And the equation that you guys get here, it's exactly the same equation as we got before. A is 17.3. If I put 17.3 here, and B is negative 0.96, so plus negative 0.96x. And if I try to match it, guys, with the equation that you have here, watch. It's the same equation. If you look at the equation. Negative 0.96x, here you go. You see the two. But this is written first here in 17.3, so it's exact same equation. The only difference between this and the previous one, the previous program, he uses AX plus B. But he swaps the A and B values. So the B becomes an A and A becomes a B. Just stick to whatever formula you use. If you use, just AX plus B, make sure to just copy the exact value of A and attach it to X and then B. Here, if you use this one, whatever B is, that has to be attached to X and then A will be alone, but you'll get the same equation, guys. You got the same value of R and the same value of R squared. It's exact same formula. Any questions about how to perform the hypothesis test using the calculator? So the highlight, of this chapter, guys, it's this formula right here. Linear regression t-test. That's gonna take care of almost everything in the chapter. And just for your information, part D, it's not like I'm asking you to list all those 3 cases. I'm just trying to explain to you that there are 3 cases. If it is a negative, there will be a left tail test, positive, a right tail test, and that's a 2-tailed. You have to choose one of them only. And we select one of them. We selected this one. Okay. Now I'm going to show you how this could be done by hand. Let me explain that to you. You might find it also not difficult to do this by hand. Using critical value approach. So first of all, we have to state HO and HA, just like we did before. correlation is significant. Correlation is significant. That's step number 1, guys. Step 2, R, find the test statistic T. Here's the formula. One minus R squared divided by N minus 2. In the book, when you do your homework online, it's if you have questions about R, it's gonna show you how to find R by hand, T by hand, the test statistic T. We already know R, guys, which is negative 0.97. And we know R squared, which is 0.94 from the calculator. So even if you do this by hand, you still need the calculator to find those answers. So if you do T equals negative 0.97 divided by square root of 1 minus R squared is 0.94. N is the sample size. How many in the samples? We have 9 children, so it's 9 minus 2. And I'm gonna pause for a minute, guys, and see if you can find the answer for me. Just use your calculator to compute this. Step 3. Okay. This is a left tail test, guys, because this is less than 0. This is a left tail test. So step 4, we're gonna, or step 2, that's step 2, and now step 3. Let me show you how we're gonna do this. Definitely we're gonna reject HO just because with the p-value approach, we rejected HO, but how do you do it with the critical value approach? He says that alpha equals 1%. All right, here's how we use the critical value approach. It's a t-test, guys. As you notice, we're putting a t. So you just go to the table that has the t-values. Look how simple it is. It's a one-tail test. It's not a two-tail test. It's a one-tail. What's alpha here? It's 0.01. I'm right here. And the degrees of freedom for correlation, guys, it's not n minus 1. It's n minus 2. So I have 9 students, minus 2 will be 7. So I have to go down to 7. So for this chapter, as you notice, the formula has n minus 2, not n minus 1. So just go to 7. Okay. So the critical value, guys, is 2.998. But because this is a left tail test, you have to use a negative sign. So it will be this is the critical value. This is the rejection region. And this is the non-rejection region of HO. Okay, so anything that falls in the rejection region will be rejected, and anything that falls right here will be not rejected here. That's a 0 in the middle. Okay, take the negative 2.74, guys. Where would negative 10.74 end up on the number line? That's a T line. It has to be to the left of negative 2.998, so it will be somewhere here, guys. It turns out to be in the rejection region, so then you reject HO. So the difference between p-value and critical value approach. For the p-value, just find the p-value and compare it with alpha. For the critical value approach, you just use alpha to find a number, which is called the critical value. And then you compare that number with the number that you had in step number 2. If this number was to the right of negative 2.998, let's say this one, guys, was negative 1.7. Well, negative 1.7 would have been here, so then you failed to reject HO. But because it's negative 10.47, which is smaller than negative 2.998, it falls in the rejection region, and you reject HO. And then after you reject HO, you say there is enough evidence to conclude that correlation is significant between the age of the child and the number of irrelevant responses. Any questions here? We will do a couple more examples after this, but if you have any questions now, please feel free to ask. Will I require that you use one approach over the other? No, you'll have the choice to use the p-value approach, guys, throughout. So if you're comfortable with the p-value approach, then that should be good. All right. Now we're going to go to the next part, the last question, which is R squared. Find R squared and interpret its meaning. And let me give you some explanation how to do this. Before I do the actual part, just in this example, I'm just going to give you a different example. Diamond weight and price. Do you guys, so now we're gonna do R squared. We're gonna interpret what R squared means. I'm gonna give you this example. I usually do this example because the students find it very easy to comprehend the meaning of R squared with this example. Just 1 second. Do you guys agree with me that the price of a diamond depends on the weight? The larger the weight of the diamond, the solid diamond, just the higher the price. So this is a fact. If someone buy a 2-carat solid piece of diamond, is going to pay thousands and thousands of dollars comparing to someone who buy like 1/4 of a carat or 1/2 of a carat. So let me just make up some data. So let's say someone buy 1/4 of a carat and it's $500. And let's say you buy 1/2 of a carat and it's $1,000. Somebody else buy another half, let's say it's $1,100. 1 carat, let's say it's $3,000. I'm just making up the stuff. 1.5 carat, $5,000. 2 carat, $8,000, and so on and so forth. The larger, the higher the weight, the higher the price as well. So you guys, I think you should agree with me that there is a strong positive correlation between the diamond weight and the price. Let's say, for example, guys, I gave you this data sets and I asked you to find R. And let's say you did R and it turned out to be 0.86. So I'm just saying we did that and it turned out to be 0.86. So you can conclude that there appears to be a positive, strong correlation between the price of diamond and the weight of diamond. Now, what I like you to do, guys, I like you to compute R squared for me. So can someone do this for me? So just take 0.86 and multiply by 0.86. What do you get? You have an answer?
0.86 times 0.86.
Yeah.
I got 0.7396.
Okay, let's make it 0.74. All right, very good. We're getting close to interpret what's the meaning of R squared. It has a meaning, very, very important meaning, and you need to understand that. Let's change the 0.74 to a percent. What would that be?
74%.
74%. Okay. First of all, R squared has a name. It's called coefficient of determination. So in the book, if he asks you to find the coefficient of determination, you just find R squared. If he says R squared, then that's good. But if he doesn't, it's called the coefficient of determination. That's R squared. All right. Let me interpret. The reason why I do diamond and price, because it's easy for students to swallow this interpretation. And then once you understand it from this example, you understand it from all others. All right. Let me tell you what the 74% mean here. It means 74% of the change in the price of diamond is explained by the change in the weight. So 74% of the times the price change, it's due to the change in the weight of the diamond. So it means there is a strong connection between the price and the weight of the diamond. As the price changes, the variation in the price could cause, variation, the variation in the weight causes variation in the price. But it does not explain the whole thing about the price of the diamond. It's only 74% of the story. So 74% of the changes in the price of the diamond is due to the changes in the weight. But that doesn't explain, just the entire change in the price. What's left from 100%, guys, if you subtract 74%?
26.
26%. So it's not only the weight of the diamond that determine, just the price of a diamond. There are some other factors. And the reason why I do this example, because students can help me list the other factors. So in particular, female students might be able to help me here. What are the other factors that could affect the price of a diamond other than the weight? 74% of the story is explained by the weight, but there is another 26% of the story that's not explained yet here in this problem. And we need to list some reasons that could affect the price of diamond. Can you guys tell me what other factors?
Cut and clarity.
Clarity, very good. Cut. What else? Color of the diamond. That you pay a big price, just for the color. Shape. I don't know. Can you think of some other factors? So these factors, guys, tell us the 26% of the remaining story. This is an unexplained variation. These are the unexplained variation. And the 74% is the explained variation between the price and the weight. So there are always, when you do linear regression, guys, there are explained factors and unexplained factors. There will be no unexplained factors if you get R equals 100%, but it's very rare, guys, that R is going to be 100%. You're always going to get a value for R squared other than 0. And as you can see, you agree with me that the weight is a big factor in determining the price of a diamond. But clarity, color, shape, and probably some other factors, whether it has been certified, just by an expert in the field or not, that's another one. People would want to buy it with a certificate. So these are all the unexplained factor. And this is what the coefficient of determination R squared is about. So how do you write, just the interpretation of the coefficient of determination? This is how you write it down, guys. And then we'll go back to our example and write down the explanation. 74% of the variation in the price of diamond can be explained by the variation in weight using the regression model. using the relationship that we came up with, the equation that we came up. Now, if you're doing your homework online and ask you what percent is unexplained, you just do 100% minus 74%, it will be your 26%. So this is what R squared is, guys. It's the coefficient of determination. It's the percentage of the variation of the y variables that can be explained by the variation in the x variable. Remember, the price is the y and the weight is the x. And when we go back to our example, the number of irrelevant responses is the y value and the age of a child is the x value. So let me just take you back to the example and show you how we explain this one. Find the value of R squared and what does it mean? Okay, so I explained, you can read all of this later. The value of R squared is called the coefficient of determination and represents the percentage of the amount of variation in y that can be explained by using the linear model y equals ax plus b. And we can say that 94% of the variation in the number of irrelevant responses on the standardized test can be explained by the variation in the age of the child. So this is the interpretation right here, guys. This is a lot of text there just for you to understand that, because it's very comprehensive handout, has all the details. So that's how you interpret that. So you say 94% of the variation in the price of diamond can be explained by the variation in its weight using the regression line. And that's it, you know, just for this chapter. There is one more thing that I want to explain to you that you might be asked about when you do your homework, but these are pretty much the questions that you will be asked to answer when you do your homework. So standard error of estimate. You see, when we use the calculator, guys, we got a value which is called S here. And we use the linear regression t-test. So what is S? It's called the standard error of estimate. It's the standard deviation of the observed y values about the predicted y values. You see, the observed y values, these are the y values right there that they give you there. So if they ask you for the standard deviation or the standard error of estimate, it's S. You use the calculator, you know, to do this one. You put your data in L1 and L2, and then you go to linear regression t-test. You run the test, it's going to give you the value of S. You can use your TI-84 to compute this value. The closer the observed y values to the predicted y values, the smaller the standard deviation. And let me tell you what we mean by observed and predicted, and that should... These are called the observed values. These are the actual values right here of y. The predicted values, guys, is when you use the equation to plug in the x value and find the y value. For example, the equation here, guys, was y equals negative 0.97x plus, I forgot what was the equation, 17.3. This is the equation. For when x is 10, we observe that y equals to 8. Well, let me see what would that be if we want to use the equation to predict the value of y. So I'm going to plug in x equals 8 in the equation, see if I get something closer to 8. So negative 0.97, guys, times 10 plus 17.3. I got 7.6, guys. You can see that. So 8 is called the observed value and 7.6 is called the predicted value. What he's trying to tell you, the closer the predicted values to the observed values, the smaller the standard deviation, the standard error of the estimate. So as you can see, there is a difference. So there is a variation. That's why there is a standard deviation. And that's what SE is about. Okay. So what we're gonna do, guys, now we're gonna do another example together test. So let me I just resumed recording. So what I was trying to say, guys, if this table pops up while doing an exercise, and the question was, check if there is a correlation or not without performing all 5 steps of the hypothesis test. Let me show you how to use this table. And actually, it does explain to you how you interpret results. It says, the correlation is significant when the absolute value of R is greater than the value in the table. Okay, can you tell me, guys, what was the value of R in the question that we just did? You still remember? It was this, negative 0.97. Who can tell me what's the absolute value of this? Absolute value means get rid of the negative sign if there is a negative sign. And if it is positive, just leave it alone. So the absolute value of R will be 0.97. Okay. Let me show you how to use this table. Remember, we said the correlation is significant. We said there is enough evidence to conclude that correlation is significant. So this table should agree with us. And look, N, what was N? 9. Sample size was 9, guys. And what's alpha in our question? Was 0.01. So just go there. You're right here at this value. The correlation is significant when the absolute value of R is greater than this value. Well, the absolute value of R, guys, is 0.97, which is bigger than 0.798. So then correlation is significant and you're done. So that's another way to check if correlation is significant or not using this table. So if you are given an option while doing the homework, just to use this table, all you need to compute R, take its absolute value and compare it with the value that you get from the table here. If R is bigger than this value, then correlation is significant. If R is less than this value, then correlation is not significant. For example, let me give you another example. Let's take N is 11, alpha is 0.05, and R is 0.683. Let's do another example here. Okay. Well, absolute value of R is 0.683 because it's a positive. Let's look at N equal 11 and alpha 0.05. 11, 0.05, right here. So 0.602, guys. Remember this number. Now let's go back to your R value. It's 0.683. Is it bigger than 0.602? Yes. Then correlation is significant. You can conclude that correlation is significant. If this was 0.58, guys, 3, then it is less than 0.602, then correlation is not significant. So this is how we use table 11 to conduct shortcut of a hypothesis summary without, just going through the 5 steps of a hypothesis test. But if you're doing your homework and then he asks you to state the null and the alternative hypotheses, then find the test statistic T and then find the p-value, you're stuck, just with the previous method using linear regression t-test. So keep in mind that table 11 can be used to test the correlation coefficient. We're gonna do, okay, so